Hello and welcome everyone. Thanks for joining me today to learn about Amazon EMR Serverless, an exciting new deployment option on Amazon EMR in preview we announced at reInvent 2021. I'm Radhika Ravirala, Principal Product Manager with the Amazon EMR Service, and I'm glad to be here talking to you about EMR Serverless. So here's a quick look at what we are going to be talking about. So we'll begin with what is Amazon EMR Serverless and why we built it. We'll also look into how it works, some of the benefits that the features it offers entails you, some common usage patterns that you can apply for your own Spark applications. We'll dive into a quick demo and we'll wrap up the session with pricing and some Q&A. So let me begin the session with the primary motivation for why we built Amazon EMR Serverless. As many of you know, with EMR on EC2, you can provision clusters of any size within minutes. EMR automatically installs and configures open source frameworks such as Apache Spark, Apache Hive, and Presto. It also gives you complete control over the configuration of your open source frameworks to optimize for performance and cost. We want to make this experience even simpler. So EMR Serverless is simple because you do not have to configure, optimize, operate, or secure clusters to run applications using open source frameworks such as Apache Spark, Hive, and Presto. EMR Serverless provisions, configures, and dynamically scales compute and memory resources required at each stage of your data processing application. With EMR Serverless, your jobs run fast. EMR Serverless includes the performance-optimized EMR runtime for Spark, Hive, and later Presto. The EMR runtime is API compatible with open source version and over 2 times faster than the standard open source. So your jobs run faster. And since you only pay for the compute time and the resources used, EMR Serverless is also cost effective. And lastly, EMR Serverless will provide comprehensive set of tools to run your applications. And by that, I mean EMR Serverless will integrate with EMR Studio, which provides notebooks and familiar open source tools such as Spark UI and Tez UI to help you develop, visualize, and debug your applications. Now let's take a look at how EMR Serverless works at a high level. To begin with, your admins and users will create a new EMR Serverless application. Once the EMR Serverless application is created, the end users can start submitting their Spark jobs. This submission can happen using multiple ways. For example, we have customers who submit jobs using Apache Airflow or using Amazon managed workflows for Apache Airflow. Similarly, they could use AWS Step Functions, EMR Studio notebooks, custom-built pipelines, or even using AWS CLI and SDK to submit their Spark jobs to EMR Serverless application. Once the job is submitted, EMR Serverless automatically provisions workers that are necessary to process your data processing jobs. And these workers are provisioned in the Amazon EMR service account, and they have the ability to reach out to your AWS resources in your VPC, as well as regional services such as S3. So this is at a high level on how EMR Serverless works. Now let's dive a little bit deeper into how EMR Serverless benefits some of your big data applications. So the goal of EMR Serverless is to provide a simpler experience. EMR Serverless is simple to use because you don't have to configure, optimize, operate, or secure clusters. You don't have to worry about instance types or cluster sizes, or about applying OS patches. You simply specify the framework and version that you want to use for your application and start submitting your data processing jobs. You still get all the benefits that you expect out of Amazon EMR, which is open source compatibility, open source version currency, and the performance optimized runtime, but without the need to manage any clusters. There is no need to guess cluster sizes with EMR Serverless because it eliminates the need to right-size clusters for varying jobs and data sizes. With EMR Serverless, you create an application using an open source framework version and submit jobs to this application. EMR Serverless automatically adds and removes workers at different stages of processing your job. As a result, you don't have to reconfigure when data volumes change, and you only pay for what the jobs require. You can easily control costs by specifying the minimum and maximum number of concurrent workers and the vCPU and memory per worker. The third benefit is you retain Amazon EMR's performance optimized runtime and open source currency. EMR Serverless includes the Amazon EMR performance optimized runtime for Apache Spark, Hive, and later Presto. The Amazon EMR runtime is API compatible and over twice as fast as standard open source. So your jobs run faster and you incur less compute costs. EMR Serverless implemented fine-grained scaling to help you save on costs. For example, your job may require 10 workers for the first 10 minutes of processing the job, and 40 workers for the next 10 minutes, and 5 workers for the next 5 minutes. With fine-grained automatic scaling, you only incur costs for 10 workers for 10 minutes, and 40 workers for 10 minutes, and 5 workers for the next 5 minutes. EMR Serverless automatically scales up workers at each stage of processing your job and scales them down when they're not required. You're charged for the aggregated vCPU, memory, and storage resources used from the time a worker starts running until it stops, rounded to the nearest second with a 1-minute minimum. Another important feature that is super important to a lot of customers is resilience. So Amazon EMR Serverless is resilient to availability zone failures. And by that, we mean Amazon Serverless is a regional service from the ground up. So when you submit jobs to an Amazon EMR Serverless application, it can run in any AZ within that region. A job is run in a single availability zone to avoid performance implication of network traffic flowing across AZs. In case an availability zone is impaired, a job submitted to your EMR Serverless application is automatically run in a different but healthy availability zone. EMR Server also enables secured shared application, and we enable that by providing a per job execution role. So with the per job execution role, you can pass an IAM role with every job that you submit to specify what resources that IAM role has access to. And this significantly simplifies your authorization model, especially in a multi-tenant environment. We'll look into more details on this feature a little bit later. Interactive applications are those that allow your data scientists and analysts to run interactive SQL queries for data exploration, and they often require a fast response times to your user requests. For such interactive application, EMR Serverless allows you to pre-initialize a pool of workers. You can start your EMR Serverless application and pre-initialize the pool of workers as soon as the user starts the application, and stop the application to stop workers when there are no interactive users that are active on the application. So if processing user requests requires additional workers than what you have pre-initialized, EMR Serverless automatically adds more workers up to the maximum concurrent limits that you specify. Therefore, by controlling the number of workers to pre-initialize and the maximum concurrent workers, you can optimize your user experience and cost for your interactive applications. And lastly, Amazon EMR Serverless makes it easy for you to switch deployment models. The same EMR release is provided for applications using EMR on EC2 clusters, EMR on EKS, and EMR Serverless. So when you build an application using an EMR release, for example, you are building a Spark application using Amazon EMR release 6.5, you can choose to run it on EMR on EC2, EMR on EKS, or EMR serverless without having to rewrite the application. This allows you to build applications for a given framework version and retain the flexibility to change the deployment model based on future operational needs. Note that as long as your Spark application is able to run within the capabilities of a deployment option, you do not have to rewrite your Spark application. So with that, let's dive into some core concepts we have introduced with EMR Serverless. Let's begin with the concept of application. An application is your entry into the EMR Serverless world. With EMR Serverless, you can create one or more applications that use open source analytics frameworks. To create an application, you simply specify the open source framework that you want to use, for example, Apache Spark or Apache Hive, the Amazon EMR release for that open source framework version. For example, if you're interested in Spark 3.1.2, you specify Amazon release version 6.5, which is the current version, and you can optionally name your application as well. In general, once you create an EMR serverless application, you can submit multiple jobs to the same application. However, there are situations that warrant creating different EMR serverless applications. Those include when you want to use different open source frameworks. For example, if you want to run Hive jobs and Spark jobs, that will require you to create a Hive application as well as a Spark applications. Other situations include where you want to use different versions of open source frameworks for different use cases. An example of this includes when you want to use a newer version of Spark for a new application without having to upgrade older applications. When you want to perform A/B testing when upgrading from one version to another. When you want to maintain logical environments to test and your production scenarios. When you want to provide logical environments for different teams with independent cost controls and usage tracking. And when you want to logically separate different lines of businesses applications, for example, finance versus marketing versus development, all these scenarios would require you to create different applications. Next, we introduce the concept of a job. A job is a request submitted to an EMR serverless application that is asynchronously run and tracked through completion. You can run multiple jobs concurrently in an application. The jobs themselves are run on workers. EMR serverless application internally uses these workers to run your jobs. By default, each application uses workers with 4 vCPU, 30 GB of RAM, and 20 GB of local storage per worker. You have the ability to customize this configuration to control performance of your applications. And finally, we have an optional feature called pre-initialized workers. This optional feature provides a mechanism for you to pre-initialize workers when your application starts up so that the workers are ready to process the request immediately when a job is submitted to the application. This is analogous to having a running EMR cluster. Pre-initialized workers allows you to maintain a warm pool of workers for the application so that it can provide a sub-second response to start processing your requests. Now that we have looked at some of the benefits and the core concepts with EMR Serverless, let's take a look at how we can apply some of the common usage patterns to EMR Serverless. We begin with data pipelines, which are the backbone for your analytic workloads. A common pattern with data pipelines is to start a cluster, run a job, and stop the cluster when the job is complete. Because the data is decoupled from compute, the inputs and outputs for each job are persisted separately from the cluster, for example, in a store like Amazon S3. Now, these steps are frequently automated using workflow orchestration tools such as Apache Airflow or step functions. You can also use AWS managed workflows for Apache Airflow or your custom built orchestration tools as well. Although automating these steps isn't complex, data engineers have to spend time trying to determine the appropriate EC2 instance and cluster size for each of these pipelines. They have to determine the AZ where the cluster is run and also handle failover. They have to test their applications when they are adopting operating system security updates. And when the data sizes change over time, they have to resize the cluster manually or use features like Amazon EMR managed scaling that automatically resizes their clusters. EMR Serverless provides a simpler solution by eliminating the need for you to handle all these scenarios. So you simply choose the open source framework and the version for your application and start submitting jobs. So you don't have to worry about instance selection, cluster sizes, cluster startup, cluster resize, topping the nodes, AZ failover, or OS updates. So as you can see from the illustration, your pipeline becomes much simpler to execute as shown in the orange boxes on the right-hand side. Let's now look at how your pipelines become simpler to run with EMR Serverless. So in this example, I have a pipeline with 4 steps. When the pipeline is kicked off, EMR Serverless application A determines that it needs to start at step A, and that requires 3 workers. It automatically provisions 3 workers to run step A. In the next phase, we have 2 steps, B and C, that could be run concurrently. And in this example, EMR Serverless again provisions the required number of workers for each of these steps and runs these steps in parallel on these workers. And finally, we have the last step, step D, which requires 10 workers. And again, EMR Serverless application A spins up 10 workers to execute step D. And once all these steps are done, the workers are decommissioned. And at this stage, you are not incurring any cost for your job. Now, we'll extend this example and take it to the shared cluster or the multi-tenancy environment and how EMR Serverless simplifies that. So you might all be familiar with the shared clusters for teams on premises using yarn queues. So this is a mechanism that traditionally on-premises clusters have used to run multi-tenant jobs on a single cluster. So yarn essentially manages your resources across clusters or queues, and the resources are shared on premises to maintain job for performance for multiple tenants. We have simplified that multi-tenancy model with EMR on EC2 using auto-scaling. So with auto-scaling, you have elastic persistent clusters that automatically scale up and scale down based on your workload characteristics. The same model, when carried over to EMR Serverless, is further simplified because your pipelines can start submitting jobs to a single EMR Serverless application, and the serverless application will determine the right amount of resources needed to execute each of those tenants and spins up the workers needed accordingly, but staying within the limits of the maximum concurrent workers that you have specified. In a multi-tenanted shared cluster environment, it is important to keep the job resources and permissions isolated as much as possible. Let's take an example of how EMR Serverless helps you accomplish that. So in this example, I have 2 data engineers who are submitting jobs to the same EMR application, Serverless application X. Data engineer 1 is submitting job A with role A, and role A has permissions to access S3 bucket A, Redshift cluster A, and CloudWatch log group A. Now the data engineer 2 is submitting job B associated with role B, and role B has access to a completely different set of resources, namely S3 bucket B and Dynamo table B. As you can see from this illustration, the workers that are spun up to run job A use role A in order to access those resources. Similarly, workers that are provisioned for job B are use the permission set associated with role B that has access only to S3 bucket B and Dynamo table B. So because these workers are spun up with a different set of permissions, they don't have access to resources used by the other job. And this is how you can keep your jobs and permissions isolated. Debugging jobs is super simple with EMR Serverless. When your users submit jobs to an EMR Serverless applications and the worker starts running those jobs, logs are continuously generated and pushed to Amazon S3. You can launch Spark UI for Spark jobs and Test UI for your Hive jobs for real-time progress of your live jobs. You can also launch a Spark History Server and the Test UI for detailed analysis even after the job completes. And the third pattern of applications that you can run on EMR Serverless is interactive applications. So with interactive applications, teams keep a cluster of instances available to support interactive analysis. So in this case, the cluster is set up and initialized with applications that wait for interactive user requests. Applications are pre-initialized so that they can immediately start processing your user requests and provide an interactive user experience. EMR Serverless enables this scenario without requiring you to manage clusters. You can provision or specify the number of workers that you want to pre-initialize when you start an EMR Serverless application. Subsequently, when users submit requests, the pre-initialized workers can be used immediately to process those requests. If processing the requests requires more workers than what you have chosen to pre-initialize, EMR Serverless automatically adds more workers up to the maximum concurrent limit that you specified. And when the requests are processed, EMR Serverless automatically reverts back to maintaining the pre-initialized workers that you have specified. And you can control when the pre-initialized workers start by controlling when to start and stop your EMR Serverless application. So for example, you can start your application when users begin interactive analysis and turn it off when there are no user requests and the applications remain idle. So here is an example of it. So in this example, I have pre-initialized my EMR Serverless application A with an initial capacity of 10, which means I have 10 workers that are ready to receive your workloads. When the workers are in a ready state, this is when you start incurring costs for your EMR Serverless application. Now, the first user A submits a job A, and that requires 3 workers. EMR Serverless application runs job A on 3 workers from the pre-initialized pool. Now, job B is submitted, which requires 7 workers, either concurrently or after job A is submitted. In this case, again, job B is run on 7 workers from the pre-initialized pool of workers. Now, at this time, if job C is submitted that requires 5 workers, the 10 pre-initialized workers are already busy executing job A and job B. In this case, EMR Serverless provisions additional 5 workers to run job C. Now, when all the jobs are finished, the provisioned workers for job C, the extra 5, are now decommissioned, and the pre-initialized pool of workers are again in a state of ready to accept any new requests. When you stop the application, the pre-initialized pool of workers are decommissioned, and at this point, you will not incur any costs for your interactive application. So with that, let's move into observability. As I mentioned in an earlier slide, application logs are pushed to S3, and service level metrics in CloudWatch will be available by GA for visibility and monitoring of your EMR serverless applications. So with that, let's dive into a quick demo of how EMR Serverless works. In this demo, we'll create an EMR Serverless application for Hive and run a Hive batch job using CLI. If you're interested in looking at an example for Spark, please check out the PySpark example for EMR Serverless on our YouTube channel or visit the EMR Serverless samples Git repository. So to begin with, I'm initializing my environment. And by that, I mean I created an S3 bucket, and I also created an IAM role that has permissions to read and write to that bucket. With that, I'm ready to create my EMR Serverless application. So as you can see, EMR Serverless application requires only two inputs. One is the type of application that you're interested in, which is Hive or Spark during preview, and the release label or the version that you're interested in. In this case, I'm specifying EMR 6.5.0. You can optionally name your application, and you can also optionally configure the auto stop mechanism for your application. And by that, we mean you have the ability to specify an amount of idle time after which your EMR Serverless application will go into a stopped state. So now that I have launched my EMR Serverless application, let's go ahead and take a look at how the application looks like. As you can see, by calling the Get Application API, I can look at the status and other attributes of my application. In this case, my application is in a created state, and it also describes the initial capacity. This is something that we have introduced only during the preview, and the auto start and auto stop configuration, which we recently added. Auto start is enabled by default. You can optionally choose to disable it. The advantage of using an auto start config is that when you submit a job, your application will start automatically without you explicitly having to start the application. Now that my application is created, let's go ahead and submit a Hive job. So I'm about to submit a Hive batch job, which creates a table based on a weather dataset that is publicly available, and followed by running a select query on that weather data by invoking the extremeweather.sql script from my S3 bucket. So in addition to the commands that I want my Hive application to run, I can also send in some parameters such as the Hive config, as well as application or configuration overrides, which includes properties that you would like to modify in your hivesite.xml. So for example, you can optionally choose to specify the number of codes and the memory for your driver, as well as the test task. And there are a set of other properties that you can modify, which you can find in our documentation. In addition to that, another notable thing in this is that you can send in a log URI, which is the location where your logs will be persisted. So now that we have defined our job parameters, we are ready to kick this job off. So as soon as you start the job, you will notice that you get the job run ID here. And I can look at the status of my job by calling on the get job run API with the application ID and the job run ID. As you can see, my application right now is in a pending state. And the reason for pending is because on the first job submission, the application gets started. And that's the message that you get here, that the application is starting. And once the application starts, your job will go into a running state. So while your application starts, let's go ahead and set up our environment so we could monitor the job using a test UI. So again, here in our documentation, we do provide instructions on how to launch the test UI during preview using a Docker container. So the instructions will include all the necessary files that you can download and launch a Docker container locally. And this is exactly what we are going to do. So in here, I am going to export the location where my S3 logs will be deposited. And then I can also build I also already have my Docker file ready here. So I'm just going to build with my Docker file, and once it's ready, I can start the Docker run to launch my. So let me go ahead and export the job ID here and kick off the Docker run. At this time, I will have the link available to the test UI locally on my local host. So I'm going to copy. So as you can see, my job is running. It has gone into a running state. I can also verify that by calling the get job run API command again. As you can see, the job is running, and you can also click on the DAG to get additional details. And as the job is running, the progress will be updated. As you can see, I have a total of 286 tasks. You can also look at the graphical view, and you can also look at the log files as they become available. Now, in the meantime, as the job is running, let me also show you that the job is actually creating a table, which is the NOAA GSORT PDS. This is a table with weather data, and the table is created in the Glue Data Catalog because by default, when you run a Hive job, it is integrated with the Glue Data Catalog, allowing you to store your metadata in the Glue Data Catalog. So now that our table is created, it is running through the query, which is the second SQL script that was included in the same job. And as soon as the job is successful, we will be able to look at the output of that job as well. So the job should be done in a few seconds, and as soon as the job is run, let's go ahead and take a look. So while the job is running, let's go ahead and take a look at the S3 bucket, where we have the scripts as well as our logs persisted. So for the purpose of this demonstration, I have two scripts, as I mentioned. One is a create table, which is just a DDL to create the table and add all the partitions in there. And then a second script that actually does some interesting querying on that weather data. And I also have a location specified for my logs when I was submitting the jobs, and this is the logs directory. As you can see, as the job is continuously run, we have the logs deposited into this application folder. So if we look at our application ID, you will notice that our application ID is right here, which ends with 1L09. If I just go into that application, you will see that I have a job that is running right now. And in here, I can find all the required logs for my job run, which includes the Hive driver logs, which has the standard error output as well as the Hive log. It's super helpful for debugging, as well as logs for my test task and the timeline data, which is used by the test UI to give you that real-time progress of your jobs. So as the job is executing, these are populated and for you to monitor the progress of your job. So let's go ahead and take a look at our job now. Now that our job is completed and has entered a success state, let's take a look at the output that it produced from that select query. So in order to do that, I'm simply going to copy the file locally and unzip it. And as you can see, I have the average daily temperatures for specific stations that I requested outputted into my output log. So this is it. This is how easy it is to get started using EMR Serverless. I hope you'll all give it a try. Hope you all got a good idea of how to run your Spark and Hive jobs with EMR Serverless application. So let's now look at how the pricing works with EMR Serverless. As discussed in the earlier slide, your EMR Serverless jobs are divided into stages, And we aggregate the compute, memory, and disk across these stages to arrive at the final cost for your job, for running your job. So in this example, I have 3 stages, and we aggregate the compute, disk, and memory across 10 workers for 10 minutes in stage 1. Similarly, we aggregate compute, disk, and memory across 40 workers for next 10 minutes in stage 2. And similarly, we repeat the exercise for stage 3. And the combination of all these stages on the aggregated compute, memory, and disk is the final cost that you will incur for your EMR serverless job. So the billing is done on a per second basis of the worker's execution time, and 20 GB of the default ephemeral storage is free, and anything beyond that is what you pay for. So today in preview, you can run your Spark and Hive jobs using CLI, API, or SDK. You can pre-provision workers for jobs to start immediately. And we have a couple of features upcoming in the preview, which is the auto stop of idle applications, as well as auto start of applications upon job submission. So here are some resources for you to get started. We have an EMR serverless blog with an accompanying video. We have a preview sign up for those interested in test driving the feature. We have extensive documentation as well as some sample demos for you to try out. So with that, I'd like to thank you all for your time today, and we hope that you will test drive EMR serverless and share your experiences with us. Thanks again.